Hi there, welcome to Telefunken. Today we have another installment in our series on the Powertran Transcendent 2000. This video features the calibration of the T2000. If you've seen our other videos, you'll know the Transcendent 2000, or T2000 for short, is a single oscillator kit-based monosynth released in the United Kingdom in 1978. This particular specimen has been imported to Canada in as-is, non-working condition. We've already gone through the machine and refurbished a number of worn components, cleaned the switches and contacts, and repaired a broken oscillator. We're now at the stage where everything's working. We can tune and calibrate the instrument prior to closing it up. So in today's video, we'll cover the tuning and calibration of the T2000. This will include calling out a number of errors in the original instructions for setting up the instrument, as described in the original articles published in Electronics Today International. Other videos on our channel cover the previously mentioned refurbishing of this instrument, including converting the power supply to work here in North America, as well as refurbishment and repair, and a modification that owners of the T2000 may wish to consider as a means of addressing what's been characterized by some as a signal-to-noise issue with the synthesizer. If any of these sound interesting to you, please be sure to check out the other videos on the channel. If you're looking for more information on the Transcendent 2000, there are a handful of good YouTube videos on channels such as Synthmania, Look Mom No Computer, Mark Jenkins' channel, and Mindburner, whose channel features classic 80s synths and includes a number of videos on the T2000. I hope you enjoy this video. Let's get started. The first step in calibrating a Transcendent T2000 is establishing the pitch spread, and this is described in page 48 of Electronics Today International, the August 1978 edition. And what we are to do is turn RV6, 7, 8, and 9, which are these four potentiometers here, entirely anti-clockwise. So these are turned all the way down. We're to set the transpose switch to the middle position and set RV5 and 4 to their central positions. So RV4 is the pitch bend, and RV5 is the tuning for the synthesizer. And so this is not got a knob on it, but is meant to be adjusted to establish the pitch, overall pitch of the instrument. So we're not going to set this in the central position, because what we want to do initially is establish a note that actually makes some sort of musical sense. And we'll do that by playing a note, a C, and what we're looking for is actually a frequency that is indeed a C. And the way we need to assess the frequency of the note that we're playing is by monitoring it on our digital oscilloscope. So the way that I'll do that is by connecting to this ground pin here, and then the high output on the instrument, which is this pin here, the third pin on this bus. And we'll see if we can get a good signal out of this arrangement. We should turn the frequency all the way up on the filter, turn the resonance all the way down, turn the sweep all the way down, VCF envelope in the central position. It doesn't really matter where these are, although I'll turn the envelope attack all the way down. We have a very short attack here. We have a high sustain, very short decay, and very short release. And when I play a note, this is what the note looks like on the oscilloscope. And this is obviously the saw, and that's the square wave. What we're to do now is tune this to a C, and the C note in question C5 is 523.2 hertz. So that's about as close as we're going to get it. 523.6. And so what we should be doing now is playing an octave below, and we are hoping that this note will actually be half the frequency. This will be a quarter, and this will be an eighth. So 523 divided by 4 is 130.8 hertz. And so if I play this note, what we should be looking for is 130.8 hertz. And we're pretty much bang on. The way we adjust this is by adjusting RV3, which is this trimmer potentiometer. And so if I turn this clockwise, it is actually decreasing the frequency. And counterclockwise is increasing the frequency. So there we go, that's 130.8. And we recheck this note, it's 523.8, and this is exactly 2 octaves below that. And so this pitch shift is appropriate. Now we adjust the transpose switch to the +2 position, bringing up the frequency by 2 octaves. And what we do now is, with the transpose switch in the +2 position, we play a note and look for a 2 octave increase relative to where we were previously. And so our C5 was at 523.2 hertz, and C7, which is 2 octaves higher, should be 2093 hertz. And we're at 2100 hertz. And so the way we adjust this is by adjusting trimmer 12, which is this one. So we're looking again for 2093 hertz. So what we've just done is we've located a error in the instructions here, because what we're supposed to be doing actually, in order to adjust the upper octaves, is adjust trimmer 13, not trimmer 12, but rather trimmer 13. So playing this note, we're looking for 2093 hertz, and we have 2146. So we turn this down, 2000 and well, I'm not changing it, and it's varying by a handful of hertz. It's really very sensitive. And this is with a 20-turn, multi-turn potentiometer. You can imagine trying to attempt this You can imagine trying to attempt this with a regular single-term potentiometer. That's about as close as we're going to get it. And so then we repeat the same thing, but with the transpose switch in the 2 octaves down position. And this time, ignoring the instructions, we use trimmer 12 to adjust the low transpose setting. Here we should be looking for 130.8 hertz. So we're very far off here. There we go, 130.8 hertz. So that and that are all in tune now. And so we've adjusted the pitch spread and the pitch of the transposition switches. Now we're to adjust the VCO shape modulation. So in order to adjust the VCO shape, the shape of the waveform, we need to monitor at the junction of R57 and R59. So we move our oscilloscope probe, and R57 and R59 are right over here. And we'll use this ground lug here. And that should give us the ability to measure the waveform on the oscillator. So here's the waveform on that oscillator. And you'll see, if I stop the oscilloscope, that it's a descending sawtooth. And the way we adjust the shape of the waveform is we turn RV14 fully clockwise, and RV14 is the shape. And so we turn this fully clockwise, and that actually gives us a very different waveform. So we go from this triangular shaped waveform to this. And what we're looking to do is adjust the symmetry of this with RV15, which is this trimmer here. And if we play a note and adjust the waveform, what we'll see is some asymmetry as the bottom part of the waveform becomes misaligned. And I'll turn this potentiometer back in the other direction and reestablish the symmetry that was there. So there we are. That's highly symmetrical. You can see that two portions of the waveform that join where that overshoot is, that spike, those two portions are aligned and joining at the same point, as opposed to being out of alignment. And so that is the VCO shape modulation aligned. So the next step is to set the VCO to transpose 2 octaves higher and play the highest note. And to set RV10 counterclockwise. RV10 is the triangle shape adjust. And it's currently all the way anti-clockwise. We're supposed to turn RV14 clockwise, which is the shape, and it is all the way clockwise. And now we're to monitor the square wave output, which is at IC13 pin 6. So another place where we can monitor the square wave is, rather than trying to tie into pin 6 on the IC, is to actually come over to the square saw switch, and here we can see the square wave right here. And that's a high note, play a lower note, and we can see that moving. So another place that you can clip onto in order to monitor the square wave output is this diode here, which is diode 13, which is also connected directly to pin 6 of IC13 and connected to the same location here on the waveform selector switch. So monitoring that, we adjust RV11 until a very small pulse is evident. And we do have a very small descending pulse at the end of this square wave. And trimmer 11 is located right here, adjacent to IC13. And if we make some adjustments here, what we're doing is changing the duration of the duty cycle ever so slightly on this waveform. And you can see as I turn it clockwise, what I'm doing is I'm reducing the duty cycle so that that downward spike there's actually a lot more space there. And what I want to do is minimize that actually. And here I go. I'm turning it counterclockwise to reduce that. And there we have a very small, very thin, narrow downward spike. And so that's that adjusted. And if I set RV14 to 5 on the dial, which is the shape, put this in the roughly the middle position. If I rotate this all the way, we should have roughly a 50-50 duty cycle, which we do. And in fact, I can measure this. We go from about a 45% duty cycle to, well, it says it's about 78%, but we know it's much greater than that. So if we set this at about position 5, what we should be able to do is rotate RV15, and we should see the mark space ratio being modulated. And again, this is a place where there are plenty of errors in the manual, because what we should be doing actually is turning, I believe it's RV9. Yep, there we go. Or The next adjustment is an adjustment to the VCA control breakthrough. And in order to make this adjustment, we move from the square wave output to looking at the output of the synthesizer as a whole. Again, coming over here and clipping onto this third pin. And what we do is we want to establish a very quick envelope for the VCA, and that means having essentially no decay, no release, and no sustain. And then we have this on repeat. And you can certainly see that if I increase the sustain. And you may be able to hear it. I'm going to turn it up. And I'm turning down now the actual oscillator, and we're looking for no control breakthrough, and we have none right now. So we have the VCO and the noise at 0. We have no VCA breakthrough, and this is to be adjusted at trimmer 22, which is this position here. So if I adjust this, you can see if I adjust it in one direction, I'm getting breakthrough. If I adjust it in the other direction, I'm getting breakthrough. And the objective here is to minimize that breakthrough. It is very, very sensitive, and I would imagine almost impossible to make this adjustment properly without a multi-term potentiometer in this location. So that's adjusted, no breakthrough. Not that I can hear at all. The next alignment is the alignment of the VCF. So we are to initially, we'll need to establish some sort of an envelope. We'll take this off of repeat. We set the filter control to keyboard, which is where it's at. We set the resonance to control to oscillator, and again, I think this is a misnomer. We set the AD sweep to 0, which is here. This is the filter sweep. Turn this all the way counterclockwise. And we play a note, and what we're looking for actually is we're looking for resonance. And I'll have to turn down the oscillator now. So we hear no oscillator, and I'll turn up both the frequency, and now I'm turning up the resonance of the filter. And what we're looking for is resonance in the form of a sine wave. And here you'll see that the output of the filter in this regard is much, much greater than that of the synthesizer as a whole. So currently we've got about a 4 volt peak to peak signal coming out of the filter. So if I play this note, we're looking at about 2.3 kilohertz. I'll go down to here, we've got about 1.2 kilohertz. And I can adjust that by changing the frequency control. And I'll tune it so that we've got about 1 kilohertz right here. So with 1 octave lower, we should have exactly half that frequency. So if this is 999 hertz, we should have 500 here. And we have 496, and we should have 250 here. We have 240. So we're a little flat in terms of our VCF tuning. And the way we adjust this is adjusting RV20. So RV20 is trimmer 20, and it is located right here. And so I should be able to adjust this until we get 250 hertz. So there we are, about 250.6. 1006. 1008. I'll bring this up a little bit. There we are. So that's that adjusted so that it is now in time. This is our Tempco resistor, which is responsible for maintaining the pitch of that difference in the filter. This last part of the adjustment of the T2000 is aligning the ADSR, that is the envelope generator for the voltage controlled amplifier. And this was a little bit tricky, and I actually had to change a component in order to make this work. The way that the ADSR generator works is that the output of IC30, which is right here, is converted into a current, which then drives the OTA that forms the actual VCA, and that's IC22 over here. The current conversion circuit is diode D30 that we're clipped onto right here. Resistor 99, which is this 3.9K resistor. R102, this 22K resistor. And then there's Q19 and this trimmer potentiometer and the resistor R105 right here. The trimmer potentiometer is connected to both the positive and negative 12 volt rail, and there's a voltage divider network that runs through R105 that turns this transistor off and on, or rather provides an offset from the output from IC30 that turns this transistor off and on to generate the current at the appropriate portion of the envelope. So it's converting that voltage generated by this IC into a current. The problem that I had was that with the originally specified resistor in this position, R105, I wasn't able to make the adjustments using this trimmer potentiometer. The schematic calls for a 100K resistor in this position, and this is a 100K trim pot. And I wasn't able to provide the appropriate offset to control the on-off of this transistor. So I'm connected to diode 30, D30, where I can monitor the envelope, and I'm connected to R105, where it is connected to the emitter of Q19, where I can measure the voltage coming into Q19. And when I play a note, I can see the attack, decay, the attack, the sustain, the decay, and the release of this note. And if you can hear that, what we're actually listening to is the premature closing of the envelope, because we can hear that note ending rather abruptly. Which we don't want. So that is something that we can adjust with trimmer 28. And we'll be able to see the voltage at the emitter changing as well. So there is a more gradual decrease in the closure of the envelope. And as I raise the offset, we want to bring this up to just the point where we can still hear the note when it closes, and then back it off. And that's pretty nice. That's a very nice gradual decay in the note. So that's exactly what we want. And now we have perfect control over the envelope. So again, this was very difficult to achieve without changing this resistor from a 100K to a 50K. So there we go. I hope that's helpful.
Well, that's all for today's video. I hope you found it useful and entertaining. Be sure to check out the other videos on the channel, including the forthcoming video on the gain stage modification we mentioned earlier. Thanks for watching.